And continuing with another example, a wheel with a 2-foot radius is spinning at 3 radians per second. What is the linear speed of a point on the edge of the wheel? Now we're definitely talking about different relationships. We're working in time as a factor, things actually moving. So the S equals R theta probably won't be our key formula here. Well, what info do we get? We've got the radius equals 2 feet. 3 radians per second is what kind of measure? That is an angle per time. That's our angular speed. Omega equals 3 radians per second. And I would say linear speed if it gave me some distance per time, miles per hour, feet per second. But if I see an angle per time, it's got to be the rotational velocity or the angular velocity, the omega. We've got R, we've got omega. We're after linear speed v. Do we have a formula that uses R and omega and v? If so, we can use that to find v. And great, we have one. V equals R omega. We're multiplying 2 feet by 3 radians per second. A case where the radians units are taken over by the feet, so it's 6 feet per second once we multiply the 2 times the 3. Don't forget that part. We're beginning to see that the key path through these problems is carefully identifying what info is given and then which formula we should use, and all along we're cautious about our units. The next example, a different wheel spins at 36 RPM, that's revolutions per minute. Through what distance does a point 5 feet from the center of the wheel move in 20 seconds? Okay, based on the amount of information given, it's starting to look a little bit hazy in terms of what this situation is actually describing. What I like to do is let's just sort through this info given, determine what each quantity represents. First of all, the 36 RPM, rotations per minute. That's got to be angular velocity. It's some amount of angle. It's not a feet per minute or miles per minute or some distance. It's a rotation. It's about how far along in a circle are we going. That's got to be omega. R, we have radius. That's the distance from center. So this point 5 feet from the center of the wheel is a reference to our radius being 5 feet. We're interested in what's going on within 20 seconds, so we're also given time. What is it that we're looking for? Through what distance does this point travel? And when it comes to distance, in the context of these problems, that is arc length, S. So we need to find S, and we're given omega, R, and T. Well, let's go through our formulas and identify any that use S. We've got S equals R theta. But this one's a no-go because we've got a value for R, but we don't have a value for theta. So we've hit a problem there. V equals S over T, our expression of linear speed. We could solve this for S. We'd get S equals V times T. We've got a value for T we could use, but we don't have V. So this formula, again, is a dead end. In this case, we have to work in at least 2 of these formulas. Remember that a formula is good to use if we can fill in all of the quantities except for 1. Our problem here is that we've had 2 unknown quantities, so these formulas are not good as is. Let's look at what our other formulas were available. We've got omega equals theta over t. I could use this because we know omega, we know t. I don't really need to find theta to answer this question, but once I do find theta, I could plug it in here, and then I have a theta to go with my r, where I could then find s. So we're keeping the same flow where we carefully figure out what information is given and then which formula to use. And as soon as we encounter this situation where we don't have enough information to use one equation, we'll have to use 2. Basically, our path goes through any formula we see where we can fill in all of the unknown quantities except for 1. So this is a formula we could use. And the way we would end up using it would be solve this one for theta. We know omega, we know t, given to us in the problem. And since omega times t equals theta, we could substitute omega t in place of this theta. And we're getting s equals r times omega times t. You could say it's a 5th valid formula that we could use, but it's really just a result of combining two of our other formulas. Do we have a different option? We do have yet another option. Thinking about v equals s over t, we couldn't use this because both v and s were unknown. But our fourth formula was that v equals r omega, and this one we could use because we knew r, we know omega. So once we find r and omega, we could substitute that in place of v. Well, let's take this equation v equals s over t, let's solve for s equals vt. Now let's do that substitution, r omega in place of v, and again we'll get to that same result, s equals r times omega times t. So whichever path we choose, they will get us to that final formula that's needed for this problem, but it was definitely necessary that we put two of our formulas together. So that's our first main point with this example. We can hit a roadblock, but this will be the path. Call on some of those other formulas that maybe don't have that quantity that we're looking for to answer the question, like in this one we're after arc length, but our first move was to go to a formula that did not have arc length, but we needed it to come up with theta so that we could use this formula or this route, both ways getting s equals r omega t. So that's what we'll use to come up with our final answer for arc length. But there are some other sticking points here that we have to be cautious with. First of all, omega, our rotational velocity, right now it's in 36 revolutions or rotations I have here per minute, RPM. I think to be technical, the wheel itself would be rotating, but a point on the wheel would be revolving. So it's a little ambiguous there. But anyways, what's not ambiguous is, just like theta had to be in radians, omega also has to be in radians per time. Now the time part, it doesn't matter, minutes, seconds, hours, but the angle part in the numerator must be in radians. It's as important as that theta must always be in radians. So omega needs to be radians per time whenever we use it in a formula. We've got some converting to do. Let's first check out the other given quantities. R equals 5 feet, that's our point 5 feet from the center, time 20 seconds. So now let's begin to do some converting. We need to convert our rotations into radians, and we also need our units of time to agree. So main rules about units are omega and theta must always use radians is the first most important rule, and the second most important rule is that the other units, whether they are in time or distance, must use the same. So where we see that r is 5 feet, anything else that's a measure of distance is going to be feet. And here our time is 20 seconds, so any place else that we see time also has to be seconds. So the 36 rotations per minute is going to undergo a few different changes. First, going to deal with the rotations into radians. I want to cancel out rotations, so I've got rotations in the denominator in the conversion factor. What unit can I come up with here? Well, I do know radians. How many radians are in a full circle? 2 pi radians. So there's a good conversion factor, canceling out rotations. Now we would have 72 pi radians per minute, but let's go ahead and change the minutes into seconds as well. Minute is in the denominator, so my conversion factor will use minute in the numerator, and I know 1 minute equals 60 seconds. Cancel those minutes. Look at what units are left over. We have radians left over in the numerator and seconds in the denominator, so we're in good shape. We've got our angular velocity in radians per second. I want to multiply across the top, divide from the denominators, but I'm keeping it in terms of pi, so I've got a 36 times 2 is 72 over 60. That's 6/5 when it's simplified, so 6 pi over 5 radians per second. So all of our measurements of time are in seconds. Feet, we only have this one place where we're measuring distance. Our omega has radians, so we're ready to use the formula. R times omega times t, 5 feet times 6 pi over 5 radians per second, times 20 seconds. We can see our units of seconds will cancel. The radian units will go and leave behind just the feet. So this multiplication comes out pretty nice. 5 cancel with the 5, 6 pi times 20 equals 120 pi feet. Seconds cancel, radians are gone, feet the unit left behind. As an approximate decimal value, 120 times pi, approximately 377 feet.